The basic component of any electronic or electrical circuit are resistors. Irrespective of the size of the circuit, usually resistors are found in large numbers. A resistor can be connected in a circuit either in a series or parallel form. Let us discuss about the total current, voltage and resistance value if they are connected in parallel. If both the terminals of the resistors are connected to each respective terminal of the other resistor, then the two resistors are said to be connected in parallel. Here we can say that the current can take more than one path, unlike in series resistor network, because there are multiple paths for the current to flow. So we can say that parallel resistor circuits are current dividers. The figure shown here has three resistors R1, R2 and R3 which are connected in parallel combination, and a supply potential VAB is supplied between the points A and B. Since the resistors are connected in parallel, the potential difference across each resistor is same as the supply. That is, VR1 is equal to VR2 is equal to VR3, which is equal to VAB, where VR1 is the potential across the resistor R1, VR2 is the potential across resistor R2, and VR3 is the potential across resistor R3. Since the voltage across each resistor is same, the current flowing through each resistor is dependent on the resistance of that resistor. The current flowing through these three resistors is different. Current in each branch of a parallel resistor circuit is different from the other. Hence, if the resistance value in each branch is different from the other, then the current in those branches will also be different. The value of that current can be determined by using the Ohm's law. So, if I is the total current entering at the node A, it has three paths to reach the node B. The current flowing through each resistance will be dependent on its resistance. So, if I1 is the current flowing through resistor R1, I2 is the current flowing through R2, and I3 is the current flowing through R3, then the current I1, I2 and I3 can be related with the help of Kirchhoff's current law. According to this law, the sum of currents entering a node is equal to the sum of currents leaving the node. So we can say that I is equal to IR1 plus IR2 plus IR3. Now let us discuss how to find the equivalent resistance. The resistors connected in parallel combination can be replaced by a single resistor with the resistance equal to the equivalent resistance of the parallel combination resistors. The voltage across each resistor is the same while the current is equal to the sum of the individual currents. So I is equal to I1 plus I2 plus I3. And using the Ohm's law, we can substitute I as V by R. So I1 is equal to V by R1, I2 is equal to V by R2, and I3 is equal to V by R3. If RT is the total resistance of the circuit, then I is equal to V by RT. And substituting all these in the equation I is equal to I1 plus I2 plus I3, we get V by RT is equal to V by R1 plus V by R2 plus V by R3. So 1 by RT is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So by adding the reciprocal values of the individual resistance, we obtain the equivalent resistance of the circuit. The inverse of this algebraic sum will give the equivalent resistance. The equivalent resistance for n resistors is given by 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by Rn. So we can say that the equivalent resistance of the resistor connected in parallel is always smaller than the resistance of the smallest resistor. Resistors in parallel combination can be interchanged without affecting the total current and the equivalent resistance. Thank you for watching the video. For more details, please visit our website or mail to us.